Um, Welcome to the webinar of Introduction to Biorefinery, Fundamentals of Biomass Conversion and Renewable Resources. My name is Humzaa Imtiaz, and I shall be the host for today's webinar. The agenda for today is that we will start off by we'll start off with a welcome and introduction, a little bit about myself and about chemical engineering life. Then we'll have a look at why do we need sustainability and to understand the um, the need for biorefineries. And then we'll have a look at understanding the biomass as a resource for sustainability. And we'll jump directly into the concept of biorefinery to understand what it is and how it can be used. And that will lead us directly into understanding the biorefinery conversion processes, including the pretreatment and the biochemical and thermochemical processes. But first things first, who am I? My name is Humzaa Imtiaz. I am a chemical engineer myself, having graduated with chemical engineering back in 2020. And since then, I have been working within the pharmaceutical sector here in Denmark. I also got a chance to work on two publications during my master's. Both of them were focused on biorefinery. So I've had a little bit of chance to work with the so I've had a little bit of chance to work with different biorefinery modeling. I also happen to be the founder of ChemEnggLife. And if you don't know Chemical Engineering Life is an online platform focused on helping different chemical engineers, students, and graduates alike to find their way in the industry. And we do a lot of initiatives to help the young students and graduates to find their way and to be able to answer their questions or any questions that they may have regarding their career or the industry. The very first initiative that we have is the talk with different chemical engineers. We host different interviews and podcasts, and you can watch our podcast on our website, and also interviews with different engineers to understand what chemical engineers do and what they are working with in their everyday life. We have different webinars like this one where you can sign up, and we have focuses on chemical engineering topics and also non-engineering topics. And just like our webinars, we also have online courses where you can sign up and get an understanding of chemical engineering and non-engineering topics as well. And finally, the initiative that we are very proud of, that is our global mentorship program. The program is about connecting young graduates with professionals so that they can ask the right questions to the right people, and the professionals can then help or guide them and then share their experiences so that they can avoid making the same mistakes that they did. So far, we have hosted more than around 500 students, participants from 13 different countries. So that's something that we're very proud of. And if you're interested, then do visit our website and sign up already today. And apart from these main initiatives, we also have something called the Chemical Engineering Chronicles, where we publish different articles about chemical engineering and the impact of chemical engineering on everyday life. We have different video series, which you can find on our YouTube channel, uh, just to bring out the entertainment side of chemical engineering, where we focus on different career paths, different tips and tricks, top 5, top 10s, with a focus on chemical engineering. And finally, we also have an online forum where you can go and sign up, and you can raise your questions, ask questions, answer questions, and share your knowledge with the rest of the community. If you're wondering where you can find us, well, you can find us on YouTube. We have around 2,000 subscribers, so you can join our community, and you can watch all of our videos, our podcasts, our old webinars, and different, and you can learn more about chemical engineering from our YouTube channel. At the same time, you can follow us on Instagram, where we try to post a bit more of the funny side of chemical engineering, and we share different, anecdotes, different posts, just to bring out, the fun part of what engineering is. You can also visit our website and become a free member. We currently have around 900 members in our website, and being a free member, it allows you to stay updated on all of our ongoing initiatives. You'll be the first one to know when a new webinar is coming up, a new course is coming up. Stay updated on our mentorship program news, And and you can at the same time join the forum and connect and talk with many of the other members of the website. And finally, also connect with us on LinkedIn, where you can join the network of around 4,000 other chemical engineers, and you can connect and learn and talk and discuss your topics and ideas. So we have a community of around 9,000 people across social media. So feel free to reach out to us. And if you may have any questions or any so do reach out and visit our website if you would like to learn more information about who we are and what we are doing right now. So jumping directly into uh, the webinar for what we heard today for the biorefinery. But before we begin, firstly, we will have to have a look to understand where we are in terms of sustainability in this world. As we all know that the population of the earth is growing. It has grown a lot. We currently have a much bigger number than what it was 10 years ago. And the the population is growing at the highest rate today as it never has been before. And that brings out a problem. The problem because with a growing population, you have a higher consumption. When you have a higher consumption, you need to meet up with that demand, and hence there is a much more energy production as well. Uh, sorry, sorry, I believe I mixed up the words. With a growing energy population, there is a much higher energy demand and consumption. And in order for us to meet up that consumption demand, we obviously have to come up with a better and more stronger ways of energy production. Energy production, which as of today is coming directly from fossil fuels, and more industries are now, using more fossil fuels and more non-renewable sources, leading to higher carbon emissions and greenhouse gas emissions, which have led to global warming and, climate change as we see today. So in order to understand the effect, we have this great equation that relates Earth's capacity with population, activity of average person, and the environmental burden. Now, the problem is that the population variable is something that we cannot control. Population is something that is going to be ongoing, that's going to keep on growing. That's not something that we can put a limit on. The activity of average person, that's also not something that we can control directly. So the only option that we have in order to reduce the environmental impact in the environment, the climate change or global warming, that is by focusing on environmental burden. Now, the main question is that how can we possibly reduce the environmental burden so that we live in a more sustainable, in a more, environmental friendly world? Then there are two ways to do it. The first one is dematerialization. The dematerialization says that we should use less resource per person. That means that the energy usage of every person should be reduced. And that's something that we have actually been doing for the past hundreds of years. Because to give you a very basic example, think of cars, for example. The cars that we have today are obviously much more energy efficient as they were 20 years ago. That's a fact. You can now travel further with less petrol today than you could 20 years ago. That's fine. You have much more energy efficient airplanes today that you had 20 years ago. Our houses are much more energy efficient as they were 20 years ago. But the problem is, even though cars are much more energy efficient, there are still a lot more cars. There are now more cars on the road than they were 10 years ago. Even though airplanes are much more energy efficient today, but there are still a lot more airplanes flying in the air today than they have been in the past 100 years. you know so that means that this is a bit of a trade-off, that even though we have started producing, we have had a lot of innovation, we have spent a lot of money and ideas on making things more efficient, but the quantity of those technologies have also increased tenfold since then. So even though they are efficient, but now everyone owns more than one car. Back in the day, 10, 20, 50 years ago, households, they probably only had one car. but now households probably have two cars. There's much more frequent air travel than what it was 50 years ago. So it's a bit of a trade-off. So dematerialization sounds like a great idea, and it sounds like it would work, but it's not something that is something that we can rely heavily on in order to reduce our global footprint. On the other hand, the other option that we have in hand, that is that of transmaterialization. And that is a great idea because transmaterialization states that instead of using the current raw materials, we should replace them with something more sustainable. Now, transmaterialization states that instead we should switch the consumption to resources that are renewable at a short scale. For example, let's say the plastic bags, the plastic bags that we use, they are not degradable, and we cannot get rid of them even for the next 500 years. And that's a bad thing, right? And that's obviously a bad thing. Something that we have known, that we have been polluting our seas, killing the fishes, killing the turtles, and whatnot. So instead of using plastic bags, we could replace them with biodegradable plastic bags to save the environment and make a shift from using non-renewable resources to renewable resources. The main benefits being that there's going to be resource efficiency, there's a much less environmental impact, and it's going to be more economic resilient. To give you two examples, think of the consumer goods that we use right now. Instead of using plastic products, you possibly could actually use bamboo toothbrushes or wooden cutlery and even coconut coir mats. In textile industry, you could transition from using petroleum-based synthetic fibers to bio-based fibers like lyocell or fabrics made from algae. Um, you could make that shift without losing the usability of these products, like a wooden cutlery, for example. Now, where I live in Denmark, I believe 5 years ago, if you bought a yogurt box, I don't know what it's called, but they used to give you a plastic spoon. Very recently, they have changed that to a wooden spoon. Now, quite frankly, as a consumer, it doesn't affect me in any way because I can eat yogurt just as well with a wooden spoon as I could with a plastic spoon. So in reality, for the consumer, for myself, it has no effect. But in terms of environmental impact, it actually has a huge impact because now the wooden spoon is, much more environmental friendly. It is much more economic resilient. It is much more, it is being made from a renewable source. If I throw it away, it's not gonna stay in the seas or it's not gonna stay around for the next 500 years. But no, it is biodegradable. And if the industry would like to make new spoons, well, they can easily do so by cutting down some more wood. So in that way, these small changes that we can bring out into the society, they are very, very helpful. So therefore, if you look at, so the idea is that we would like to go away from non-renewable resources towards renewable resources. In terms of the renewable resources, you have your sun, you have tides, hydropower, then you have wind energy, and you have biomass. And in the non-renewable, you have coal, natural gas, and crude oil. We all know that there is only a limited amount of coal, natural gas, and crude oil in Earth. Therefore, after a certain amount of time, we would have exhausted all of our resources that we have. On the other hand, solar energy, hydropower, wind energy, they are unlimited sources of power. We can use them as much as we want. We can use them for as long as we want. And unless the sun blows up tomorrow, we can expect that to stay around for a while, right? So, but the limitation is that the solar energy, wind energy, and hydropower, they can only be used to produce energy. They can only be used to produce electricity, for example. They can help us turn what do you call those? What's the word? Like the things that turn to make electricity. We can use them for those purposes. We can use solar energy for solar cells and everything. That's fine. But the biomass, on the other hand, can do the same thing as these, but at the same time, biomass can also be used as a raw material to produce high value products, just like petroleum refinery. Like I said earlier, like a wooden spoon, for example. I can't make a wooden spoon using solar energy. I can't do that using wind energy. I can't do that using hydropower, but I can do that using biomass. Uh, I can't make medicine from solar energy directly, but I can do that from biomass. So therefore, biomass is incredibly interesting and incredibly useful because it allows you to be able to produce different different high value products as compared to many of the other renewable resources that we have. So the question that comes to the head is that what exactly is biomass, right? Unless you don't know it already, biomass is any organic matter which can be used as an energy source and is available on a recurring basis. That's how we define a biomass. Uh, as of right now, the main groups of biomass that we have, the categories of biomass that we have is wood, crops, and waste. Wood is literally any wood. Crops, it could be wheat, maize, rice, sunflower crop, energy crops, and then you have your waste. The waste could be the food waste, animal waste, industrial waste, manure, all of that stuff. And so therefore, and it's not something unheard of because biodiesel has been known to be made from vegetable oil, from rapeseed oil. It can be made from waste cooking oil. Polylactic acid can actually be made from corn. Polyols can be made from wheat. Succinic acid can be made from biomass. Glycerol is another main product. So there are actually a great deal of different final high value products or materials and biodiesel and biofuels that are been known to be made from different biomasses. And at the same time, um, instead of using crops, for example, because when you start using crops, you are directly competing with the food market. So therefore, instead, the governments have encouraged and have highlighted the fact that waste and lignocellulosic materials, which includes wood, straw, energy crops, agricultural waste, they can be used since they will avoid the competition with the food market. But either way, it's a great source of energy, great source of energy that can be used for to produce high value chemicals. Not only energy, but also high value chemicals. And the main benefit of biomass is that it offers a closed loop system. The reason it offers a closed loop system is because let's say trees, for example. When trees are growing up, they actually take in the carbon dioxide from the environment, and then at the end of their circle, then they release the carbon dioxide into the environment once again. But the net emission is zero because they're only releasing the carbon dioxide which they have used up throughout their lives. So therefore, we won't end up getting a higher amount of carbon dioxide in the environment than what we had before we cut down the trees. On the other hand, if you look on the right side, in the fossil fuel scenario, we are actually directly adding additional carbon dioxide into the atmosphere without any ways of reducing it. So therefore, the biomass usage as an energy source is much, much, much better in compared to a fossil fuel energy source. And there are different types of biomass that we can, use actually. There's the agricultural, forestry, animal waste, energy crops, aquatic, and urban and industrial waste. Uh, the very first one, the agricultural residues. It is all these are the byproducts generated from farming activities. It could something be like straw, husks, corn stover, sugarcane residues, nutshells, and anything, literally anything that uh, basically any waste that you would have from agriculture, right? If you are a farmer and then you have done your work and you have sold your crops and so on, anything that's lying at the corners, something that you cannot use, something that is utterly useless for you to work with, that is biomass, and that can actually be used as form of energy in the industry. There are obviously a lot more as you see on the screen on the right. And it has multiple uses in the industry. The first one being that it can be used for bioenergy generation, either through combustion or through anaerobic digestion. uh, you can use it for to build different materials like biocomposites, bioplastics, and even specialty chemicals. uh, and the main benefit that comes out of it is that obviously that the agricultural residues, it's a very cheap raw material, right? I mean, it's just waste. Secondly, it's a waste. Uh, what else would you do with it? You're probably going to throw it away. You're probably just going to, get rid of it. But now you can utilize it. So now we have less waste going around in the world. And finally, it also offers a great economical option, because let's say you are a farmer. Now, instead of just throwing away the waste, you can actually have an additional revenue stream from the waste that you normally would have thrown out. So that's also like one way to look at it. Another type of biomass that we can have is the forestry residues, and that's basically what it sounds like and what it looks like on the picture. These are the leftover materials from forest operations. uh, like anything that is not good enough for making your fancy furniture, that something that just left behind in the forest, or just a tree that's about to fall down, you can use that as a biomass energy source. And it's actually one of the biggest sources for biomass, and it can be used for bioenergy. You can use it for wood pellets, direct combustion, or gasification to generate heat and power. uh, and the funny thing is that biomass is actually one of the oldest energy sources in the world, because even in back when we had no industries or anything, people used to burn wood to generate the fire, to make fire and to generate heat. So in reality, the biomass or wood burning and biomass as an energy source outdates the industrial revolution and more or less all of our civilization. So that's just the one interesting thing to remember. But coming back to it, so you can also use the wood forestry residues for bio-based products, and you can use it for raw material for the pulp and paper industries, lignin-based additives, and the construction material. And it has a huge environmental impact, because firstly, you're getting rid of waste. And imagine just having wood lying around, but instead you're making use of it, and using it to build actual final products that you can go and sell into the market. And then you have your energy crops. Now the energy crops are crops that are non-food plants, but are specifically made for biomass production. To name a few of the species, you have switchgrass, miscanthus, poplar, willow, and jatropha, and there are quite a few on the pictures on the right. The benefit is that you're not competing with the food market, because, for example, instead of using, let's say, I don't know, soybean oil, for example, because soybean oil is used for food, if I'm not wrong. But instead of using soybean oil, then you can use, I don't know, switchgrass instead. uh, to then you're not directly competing with the food market. Basically, sugarcane, for example. Now, sugarcane is a food plant, but people are dependent on it. People are going to eat it afterwards. But instead of using sugarcane as a form of source, you can replace it with something else that is a non-food plant, and then you're not directly competing with the food requirement. And you can obviously use it for biofuels. It is used for bioethanol, biodiesel, and advanced biofuels. And you can also use it for biochemicals, for bioplastics, bio-based solvents, and other chemical precursors. And another benefit is that, if you have a land that is not suitable for food plants, or it's not suitable for food production, then you can actually use it for energy crops. Uh, the more plants you have, the better for the environment. So that's an added bonus. And also, most of these non-energy crops, they tend to have a very high yield per hectare, and they can easily grow on marginal lands which are unsuitable for food production. So that's also a huge plus that we can make use of. And then we have organic waste. And organic waste is basically anything, from households, from industries, and from municipalities. It could be food scraps, animal manure, the sewage sludge, and industrial organic byproducts. So for example, if you ended up putting too much on your plate and you can't finish your plate, the food does not necessarily have to go to waste, but rather we can actually use that leftover food to for biogas production or for fertilizers. Uh, the very common use of organic waste is biogas production, in which through anaerobic digestion, the microbes can convert organic waste into biogas, which is a renewable energy source. And the biogas can either be used as a biogas, or biogas can actually be converted into biomethane, which can also be used as a fuel. On the other hand, you can also use organic waste as a form of fertilizer, because the digestate from the biogas production is rich in nutrients, and then that nutrient can actually be used in organic fertilizer. So again, it completes the circle. You again have a closed loop, because you have organic waste, you have your fuel, but the leftovers can be then sent back into your energy crops, for example, and then making a better uh, fertilizer, or for your energy crops. And imagine, like I said earlier, that instead of wasting your food, now you have use for it. Instead of sending all of our waste, our food to landfills, we now have a better use of it to produce energy, to produce biogas, to produce fertilizers. And then at the same time, you can in cities, for example, there tends to be a great deal of problem with rats and all these other rodents. That is also something that can be solved by getting rid of throwing away organic waste in streets or in the bins, but instead taking it away for to be used for other biorefinery operations. And then the last one that we have on the list, that's algae, that's aquatic. Uh, Algae includes microalgae and microalgae, and they are normally, used as biomass in multiple different areas. Firstly, it can be used for biofuels, biodiesel, jet fuel, and bioethanol. And secondly, it's actually also used for high value products, including pharmaceuticals and nutraceuticals and cosmetics. And having algae as a biomass actually has a great deal of benefits. Firstly, because it can grow in non-arable areas. That means that it will not compete with agricultural land. So if you have a pond, or if you have a place that you're not going to use, or you don't want to use it for agriculture, you can use it for algae. And it's a known fact that algae uses a lot of carbon dioxide while growing up. So in reality, uh, we can actually use that for our advantage for carbon capture purposes. And once again, then you again have a circular economy principle, where you will where the net carbon emission could possibly be reduced if algae, takes in more carbon dioxide than it lets out in the biorefinery process. So again, it's a huge benefit that we can make use of. So that was all about the different biomasses that we have and what sort of the uses we can think of them. But then once we have that understood, then we can jump into the idea of understanding the concept of a biorefinery. I mean, very simply, a biorefinery is a refinery which converts biomass to energy and other beneficial byproducts. So you have your biomass, it goes into the biorefinery, and then you have on the other side you have your either energy, or you have high value products coming out, and that's basically a biorefinery. A biorefinery is and then you can have any type of product. You can have a low value, high volume product, such as transportation fuels. You can have a high value, low volume products, or specialty chemicals like pharmaceuticals. And it's basically just like a petroleum refinery, you know but instead of using fossil resources, we are now using biomass. So that means that instead of using crude oil to make fuel that fuels my car, I would rather be using waste cooking oil to make biodiesel, and then use biodiesel to run my car. And like I said earlier, it has no effect on the consumer at the end of the day. You are still getting the same output. You're still getting the same, activity. You're still getting the same everything, but only the source of that product has been changed to something more renewable. And there are three types of biorefineries. I'm going to very briefly touch the idea here. But the phase one biorefinery, it is one of the most simplest biorefineries that you can have. A phase one biorefinery focuses on producing one product, and that's it. Typically, biofuels like ethanol or biodiesel. Um, it has only one feedstock, one very simple one, and doesn't necessarily have very complex thermochemical or biochemical, but rather it uses very simple thermochemical and biochemical processes. Like you think of it as a very simple biorefinery manufacturing facility. Obviously, it has very low complexity, and but at the same time, having only one product puts a lot of pressure on the final product. There's not a lot of diversification. There could be economical constraints if your product is not doing very well. Uh, so these are some of the considerations that we may have to look at if you're working with a phase one biorefinery. But then you have a phase two biorefinery. A phase two biorefinery has a wide array of different products as compared to a phase one. In phase two, you actually have single feedstock, but that single feedstock is used to produce multiple high value products. And then at the same time, phase two, the biorefinery could use a, 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 um, a bit more of a mixed, more complex feedstocks. It could be agriculture, forestry, even organic waste, which would then in turn mean that you would have to use a more complex thermochemical and chemical processes, and even a lot more complex pretreatment of your feedstock. If you have more products, obviously it's better economic wise. It's better for your market demand. You can easily, you're not as flexible as a phase one biorefinery, but you're still more profitable than a phase one biorefinery. So that's essentially what you would do as a phase two. Then the last one, the phase three. The phase three is the most advanced biorefinery that you can have. It's a fully integrated and designed to maximize the value of biomass. You would end up working with a lot more, how do you say it, a more complex feedstocks such as algae, municipal solid waste, and even CO2. And then you would have a much more high value bio-based products, even pharmaceuticals or food ingredients. And obviously, the phase three is the most complex of it all. The king of biorefineries, you could call it. They represent, the highest amount of. You will maximize your profitability, maximize your usage of your feedstocks, and maximize the technology advancement that you possibly would have. But having said that, it would also mean that you would have a much more complicated thermochemical and biochemical processes, even a combination of the two, a much more complicated pretreatment, a much more investment. The only downside then would be that in comparison to a phase one and phase two, your investment in phase three would be a lot higher. Your equipment would be a lot more advanced, lot more complex, and with that comes a great deal of risk as well. I found this great diagram from the internet, and I would strongly urge to check out the link and read up on the article, because they really give a very good description of the phase three biorefineries. But just to very briefly, there's a great market demand. There is optimism for the industries and so on. And the strength, obviously, it's the strongest of the three. You have a low carbon footprint, high value based products, and and a high biomass availability. But there is high risk, there is uncertainty, there is a high energy, there is a high capital cost, and there would definitely be scale up issues. That is something that that might also come up in phase one and phase two, but it would be a lot more complicated in phase three. And so now that we know what a biorefinery is, there are actually four types of products that you get on the other side of a biorefinery. The very common product, that is biofuels, which includes ethanol and biodiesel. Then you have biochemicals, which could be lactic acid, succinic acid, which are actually used for producing a very high value products. Succinic acid is even used for the pharmaceutical production. Biomaterials like bioplastics, biocomposites, and then finally you have bioenergy. The bioenergy is basically from biogas or biomass combustion, for example. So these are like the four horsemen of biorefinery, the four products that you can get. So anything that you get, you can either categorize them into these four categories. And again, biorefinery is not an alien concept. It's something that we have had for a very long time around the globe. In Brazil, there is large-scale production of bioethanol from sugarcane. Many European nations, they have started focusing on anaerobic digestion of their food waste and into valuable energy source. The United States are pioneering bioplastics from renewable feedstocks. So it's not unheard of and it's not uncommon anymore to hear of biorefineries. And you'll find that there are a great deal of research papers. There's a great deal of PhD research projects going on around the world where people are focusing extensively and actively on biorefineries and using biomass as an energy source, as a feedstock to produce high value products. Uh, Obviously, it's not as advanced as we would like it to be, but still, we have to start somewhere, I guess. And you'll find that majority of the countries with a very strong regulatory network, they typically are more focused on biorefineries as compared to many of the other countries who may not enjoy the strong regulatory framework. But even then, maybe in the next few years, we will be able to see the shift of a strong shift of going from the fossil fuel industry towards the biorefinery industry. But having said that, now we're going to jump into the key biorefinery technologies and applications. So within a biorefinery, you have to remember that things don't magically come in and go out on the other side, right? Something has to happen in the middle. Uh, in a biorefinery, there are different steps that we have to perform. When the feedstock comes in, typically there's pre-treatment. The reason that we do pre-treatment is that it could be that there's a very high water content, so we need to dry our feedstock. Then we need to clean it up. We need to, I don't know, like chop it up, they smaller, chirp it, make it into smaller, powder or whatnot. And then once that is done, then we need to perform another form of pre-treatment that is more focused on breaking down the shape, the size, the chemical composition, so that it's easier for the enzymes to break up the the cellulose and hemicellulose and to convert that into glucose and xylose, for example. And then you would have a conversion, which would be a reactor, analogous to a reactor. In a biorefinery, you would have a conversion process either through a thermochemical or a biochemical, which directly converts biomass into either energy or an actual product. And then you would have your downstreaming right after. Now, for the purpose of this webinar, we're going to have a look at the pretreatment and the thermochemical and the biochemical processes. I'm not going to go in detail about the downstream processing because that's something that's very common, that you're just purifying. That's not something that is specifically relevant or specifically built for biorefinery. You can use the same principles of any other basic process design knowledge in a biorefinery than that you would in a fossil fuel production manufacturing site. But the pre-treatment methods are slightly different because they are focusing on very different aspect of the biomass feedstock. Obviously, I'm not going to go through each and every one of them, but I did pick a few of them that we're going to look in detail just to give you an idea about how and why we perform pre-treatment. The very first one, that is the physical pre-treatment of biomass. And the reason that we do a physical pre-treatment could be to modify the size and structure of biomass to increase the surface area and also reduce the crystals of cellulose. The very first method, that is mechanical milling. It's like milling is like a machine that you put the biomass in and it reduces its particle size. Obviously, the smaller, the more the surface area, the more the reaction rate, right? So that's the whole idea that we're aiming for. The more the surface area, the more effective enzymatic action, and we can aim for a more enzymatic activity. And it's normally done so for wood and agriculture residues because it's broken down, because it's stiff, think of a wood or like a wood log is brought in, and then it's milled and it's broken down into smaller pieces so that it's easier for the enzymes to attack it. And then you have something called a steam explosion. What we do is that we have biomass, it's put in into the reaction chamber, and then you blast it with high pressure steam, and then rapidly depressurize it. It breaks down the lignin barrier in your ligno in your I yeah, it breaks down the lignin barrier on the lignocellulosic biomass, and then it allows you to easily hydrolyze hemicellulose and cellulose. And then the last one is extrusion. This is like another physical process, and then it's like a long screw extruder, and you put in the biomass, and then it at high pressure and high temperature, and you end up disrupting the structure of your biomass feedstock. But unlike the physical, we also have a chemical pretreatment. Now, chemical obviously is when you are trying to attack the chemical composition of biomass. It could be to dissolve lignin or hemicellulose, so that it's much easier for your enzymes to attack cellulose and convert that into glucose or xylose. So the very first one is the acid pretreatment. Now, the acid pretreatment is dilute sulfuric acid, for example, and you hydrolyze hemicellulose into simple sugars. And that means that your cellulose is then fully exposed and can be directly attacked by your enzymes. On the other hand, if you use your alkaline pretreatment, which is normally done so by using sodium hydroxide or ammonia, it then attacks your lignin and acetyl groups, and which also improve the cellulose digestibility by removing the lignin. So the idea is that if you use the acid pretreatment, then if you would like to attack the hemicellulose, then you use the acid pretreatment. If you would like to attack the lignin barrier, then the alkaline pretreatment is what is required. Sometimes it could be needed that you need to mix up the two, a mix of both physical and chemical pretreatment, and that's where we have ammonia fiber expansion. It works like steam expansion, but with ammonia. You have liquid ammonia at high temperature and pressure, and then you rapidly depressurize with your biomass. It removes your lignin and your hemicellulose, and it's easier for the enzyme to attack your cellulose. And then you have your liquid hot water. Biomass is treated with hot water under pressure. It once again, it targets the hemicellulose and allows the cellulose to be attacked by the enzymes. The whole idea of pretreatment, obviously, then is to be able to attack the lignin barrier, the hemicellulose barrier, so that it's easier for our enzymes to attack the cellulose and convert that into fermentable sugars, for example. So exactly. So that's the reason why we're doing pretreatment. So what you see on the left hand side, right, is we have lignin, and then within that barrier you have hemicellulose, and the cellulose is all around it. So we need to get rid of the lignin barrier and the hemicellulose so that it's easier for the enzymes to attack the cellulose, which can then be converted into fermentable sugars like glucose and xylose, and then take that into fermentation process, and then for the yeast to attack and then be able to take it away. Yep. So that then you obviously have so the yeast can ferment it and then make into a biofuel. And then the more effective your pretreatment, the less money and power you would have to spend in your downstream processing. The weaker your pretreatment, the more time and effort you would have to spend in your downstreaming to purify your stream. So therefore, it's actually very, very, very important that the pretreatment is done efficiently and as effectively as possible. But once you have performed your pretreatment, then obviously you need to convert your biomass into your energy or into your final product. And there are two ways to do that. The first one is thermochemical, and the second one is biochemical. In the thermochemical conversion process, we make use of heat and chemical reactions to convert biomass feedstock into our final product. In thermochemical, the very first one is pyrolysis. Pyrolysis involves heating biomass in the absence of oxygen. And what you get is you get bio-oil, syngas, and biochar. Biochar can then be just used for soil amendments, and you can use bio-oil or syngas as, as for example, fuel, energy, and whatnot. So it's sort of like a thermal decomposition process. We do that for pyrolysis. And there are three types of pyrolysis. There's slow pyrolysis, fast pyrolysis, and flash pyrolysis. Slow is done at low temperatures, but for a very long residence time. The fast one is done at around 500 to 700 degrees Celsius, and the flash one is done at very high temperatures for very short periods of time, all depending on the final product, on the feedstock, and what is that you're working with. And obviously, before you perform thermochemical, you need to make your product's feedstock go through pre-treatment. Uh, Typically, it could be that you need to remove through a physical pre-treatment. For example, break it down into smaller structures, smaller size, like mechanical milling, for example, chirping, or it could also be to dry it to remove the water content. Another process is gasification, and gasification happens at high temperatures with controlled oxygen. And what happens is that the carbon in biomass reacts with controlled oxygen, and it creates syngas, which is a mixture of carbon monoxide and hydrogen. That mixture can then be further uh, either be used into creating electricity, or it can actually be used for, let's say, for the Fischer-Tropsch diesel process. And that's actually another process that utilizes this thermochemical process from biomass. And the one that you see on the right, that is actually the Fischer-Tropsch synthesis process. And then the last one, thermochemical process, is combustion, a very simple and a very old process in which we burn the biomass directly to generate heat or power. The only downside is that you can't store the heat. So that means that you would have to make use of it right away. And that's what we do. We do use it to turn the steam or turbine and to make the generator and make electricity. So that's what we do for combustion. Now, coming on the other side of the table, we have the biochemical conversion. Now, unlike thermochemical, biochemical relies heavily on biological agents to break down biomass into your desired product. The very first one, the very well-known name in the industry, that's fermentation. That's where microorganisms convert sugars into ethanol, biobutanol, organic acids, and you name it. A very long process, but a very, very well-established process in the industry. Uh, another method is anaerobic digestion. That is normally used for food waste, animal manure, crops, and microbes in the absence of oxygen convert the waste or the biomass into biogas. And it could be that the biogas can be directly used as a source of energy, or it can be converted or refined to create biomethane. And then biomethane can then be used as a gas or as a fuel afterwards. And finally, we have enzymatic hydrolysis. And enzymatic hydrolysis is also a critical step in breaking down the cellulose into fermentable sugars, which are then actually converted into fuels or chemicals. So in reality, enzymatic hydrolysis on its own does not necessarily convert your biomass into your product, but rather enzymatic hydrolysis itself is a pre-treatment for before fermentation. Because like I said earlier, within your, as you see on the diagram as well, that you have biomass. Within you have your cellulose, hemicellulose, and lignin. If you remember, like I said earlier, in your pre-treatment, in acid pre-treatment, we can get rid of hemicellulose. Through alkaline pre-treatment, we can get rid of lignin. And then when we perform enzymatic hydrolysis, it breaks down. Hemicellulose is broken down to xylose, and whereas cellulose breaks down into glucose. And then we can perform fermentation, and then fermentation in the yeast can convert glucose to ethanol. And then ethanol can then be distilled in downstream processing and can be purified to get 100% ethanol. And that's essentially how you would make use of the pretreatment, conversion, and downstream processing in a biorefinery. There. But you see, as you may have noticed already, that biorefinery and biomass offers a great deal of flexibility, a great deal of advantages, and a great deal of uh, advantage of benefits for not only for the consumers but also for the industry and for the environment. But obviously, it does not come without its own hurdles of challenges. Um, because there is a great deal of feedstock challenges associated with biorefineries. The very first challenge, obviously, is the availability. The very first is the availability of the feedstocks. It is because, in contrast to fossil resources, which are normally found in rich deposits, biomass is widely distributed geographically. Like I said earlier, if you have energy crops, you would need hectares and hectares of land to be able to grow. On the other hand, if you mine in one area, you would be able to get a lot more coal or natural gas and whatnot. At the same time, if I picked two stones of coal, uh, they will most probably be identical in composition, chemical composition. In You can't say the same for biomass. The reason being that the biomass differs a lot in moisture content, composition, energy density. You can't expect the same stuff from forestry waste that you would expect from an agricultural residue, and that is a challenge. So the standardization of biomass feedstock could be a challenge in comparison to the fossil fuel. And finally, there tends to be a relatively high water content in biomass. Like in grass, there's almost 90% water, and that is obviously much more expensive in terms of pre-treatment, in terms of transport, in comparison to natural gas or petroleum. Also, there's also a great deal of economic and market challenges, and that is something that we could argue could be fixed with time. But as of right now, if you are competing with the petroleum industry or the fossil-based products, then obviously you have to remember that biorefinery does not have a strong established market, but rather the fossil fuels, fossil fuel-based products do have an established market, and they have an established infrastructure. They have an established design, process designs, process optimization techniques. They have an equipment that has been, designed and optimized over time, over periods of years, to suit their production processes. The same cannot be said true for biorefineries. So therefore, there is a great deal of uneven playing field between the biomass and fossil fuels. When we talk about scalability, that could also be a hurdle because obviously biorefineries could require a high capital cost. Again, something that we might learn through time, that what works, what doesn't work. But as of right now, since we don't have that many high functioning biorefineries, that still poses a great challenge. And like I said earlier, that if you have multiple sources of your biomass, let's say you have forestry waste, you have algae, you have waste, you have, for example, what's called agriculture. You can't find all of that in one place, so that would mean that you would actually have to. You won't be able to find that in one place, so you would obviously have to find that from different sources, and that could also be quite difficult in terms of supply chain logistics for feedstock collection. And obviously, the market dynamics could also have a huge impact on the final products and the prices. And then, of course, the policy and regulatory landscape also poses a great challenge for the biorefineries. Uh, there are incentives which have helped a great deal to the biorefineries, like, for example, carbon tax or carbon emission taxes. It could be that the incentives or subsidies for biorefineries could make a great impact, because then it would be easier for them to compete with an established market. But even then, it would require a lot more for them to break the market and enter with their own products. And since bio-based products are relatively new and they're being made from something that has not been done before. The approval of bio-based products is quite difficult, can be quite complex, and can also delay the market entry, especially when we talk about pharmaceuticals or the food industry or within the very regulated industries. And also, as of right now, there is a lack of harmonized standards for biomass. What is considered to be pure in EU might not necessarily be the same standards in the US. And these differences of opinion could also lead to a great deal of gaps in the trading sector. But having said all that, we have to remember that the global trends across the world has been quite positive towards uh, biorefineries. So in that regard, it does make sense to look around and see that more and more countries are now are investing more and more money and time into biorefineries and trying to move towards a more renewable energy production as compared to using fossil fuels. So that does give us hope, and that does shows that the world is ready to move into that into that way, as unlike what they have been doing in the past. So yep. So thank you so very much. That was actually all for the webinar. And I hope that you got a bit of an idea, at least as a fundamental knowledge about what a biorefinery is and what a biomass is, and what sort of production processes there are in a biorefinery. Uh, and do stay tuned for future webinars by Chemical Engineering Life, where we'll be delving more in detail about about biorefineries and their processes. So do visit our website at www.chemenglife.com, and then there you'll be able to see more webinars, upcoming webinars, and if you find them interesting, then do remember to sign up for them as well. But thank you so very much for listening and for attending, and I hope you all have a great day, and I'll see you soon in our future webinars. Thank you.